Welcome everyone. Today on the bench we're going to talk about resistors. Well, this is a very broad field of electronic component, so we're going to narrow it down. You have thermistors, which are temperature sensitive, light sensitive, variable resistors such as potentiometers, and a host of other types. But we're going to narrow it down to just fixed resistors. And to be even more specific, it'll be 5 different types, which we'll talk about as I get on into the video here. And I have an assortment of various different types sitting here that we'll take a look at. Now, one thing I will say is that some resistors were harmed in making this video. I did break some open and sand some down so we can take a peek inside to see what's going on. Now, you might think resistors are a boring subject. They're just passive components that resist the flow of electricity depending on how they're made, and they have a certain value of resistance in ohms. But there's a lot more to it than just that. When you think of resistor, you generally think of, well, what's its resistance, and probably secondary, how much power can it dissipate. But like I say, there's a lot more to it than that. There are quite a few different issues you have to think about when you use a resistor in an electronic circuit. It could have a detrimental effect on the circuit if it's designed for high precision or high frequency or something like that. So here's a few things you need to consider. First is the temperature coefficient, sometimes called TempCo. And resistors, they can vary somewhat depending on their temperature. In most cases it's not very much, but it's just something you have to take in consideration, especially in a high precision circuit. The second item in the list is temperature rating. Different types of resistors can handle higher temps more than others. For example, a Wirewound resistor with a ceramic coating, those can get a lot hotter. They have a nichrome or some other type of wire inside, and those generally can handle a lot more heat than such as a carbon composition type resistor. So that's another thing to consider. Next is voltage coefficient. As the voltage changes across the resistor's terminals, of course the current will change through the resistor, and that actually can have some effect on the resistance. And if the resistance changes with the voltage across the resistor, it means you have a nonlinearity, and that can introduce distortion into your circuit. While this is a very minor thing, if you're designing a very high precision, low distortion circuit, it's something you have to take into consideration. Next is the maximum voltage. Normally you would think the voltage across the resistor's terminals would be limited by its power dissipation, but in some cases where you have very short duration pulses where the RMS voltage is low and thus the power dissipation would be low, you can have very high momentary voltage drop across the resistor, or with a high value resistor where you can have a very high voltage across the resistor. With some of the smaller size resistors, you can have a situation where the voltage gradient is high enough to arc over across the resistor's terminals instead of having the current flow through the resistor itself. And that can be a serious problem. One thing you can do to remedy that is put several resistors in series. For example, if you have one 100K resistor and you're having an issue where the voltage is too high, you're exceeding its maximum voltage with a train of pulses or whatever in your circuit, you can take 5 20K resistors and put them in series, so you are actually making that distance larger. And you'll see that used in devices like multimeters, where they'll have several series resistors to help widen the gap, because you'll have these devices able to measure upwards of 1,000 volts, and you want to have a better safety clearance there. Next is tolerance. You'll have your resistors, usually these days they're 5%, 2%, 1%, or even tolerance figures under 1%. Not much to say on that other than if you're building a precision circuit, you want to put a precision part into it. Next up is reactance, and that could be inductance and capacitance. Because of the way resistors are made, some different types can have inductance, so you won't be able to use them, for example, in a RF type circuit. For example, a Wirewound resistor has a coil of wire, and that will have some inductance to it. So those won't perform very well in a high frequency circuit. And in some cases, you have to deal with capacitance. Just like any other electronic component, you will run into these, as they're called, parasitics, that can affect how the device works in your circuit. Last but not least is noise. When an electric current passes through different types of materials, they can produce noise. In a high gain amplifier circuit, you want to minimize the noise as much as possible, so you want to select a resistor that has the least amount of noise. Noise can also be a problem in higher value resistors, so in certain amplifier circuits you want to have as high as impedance as possible within the circuit, but you're limited by the noise that could be produced in the resistors of higher values, so you have to choose a lower value. Now when I cover an electronic component, I have to assume that not everybody knows everything about electronics. I know most people who watch my channel probably understand this stuff already, but it's good to get everybody up to speed here. So yes, resistance is measured in ohms, and resistors use color codes. So I'll just show you a book here, the Radio Shack Electronics Data Book, and it shows you different resistor types here and how they use the color codes and what the value of the color codes are. So on a typical resistor you have the first digit, the second digit, and the multiplier. And then there's a tolerance band. And uncommon, I've never seen it before, is a failure rate band. So let's use an example here. I don't know if you can see this very well, but this here is a green, blue, orange, and gold resistor here. So that's, obviously it's 56K. So if you look here, green is 5, blue is 6, and then the multiplier, which was orange, so you multiply it by, where's orange? 1,000, so it's 56,000 or 56K. And the tolerance band was gold, so you just follow that over. It's a 5% resistor. So not really much to say on that. It's familiar to most people. Here's a few types of older resistors you might run into. They use the body color as the first digit, and then over here is the second digit, and the multipliers here. So you run into some of this weird stuff with older components. And I should mention the tolerance band, usually at the end. Now on surface mount resistors, they don't have the coloring codes, they have a number. So you have to be careful because those can get you sometimes. So if you see, like on a little surface mount resistor, 101, that means it's a 100 ohm. So it's 10, and this tells you to put another 0, so it's 100. And if it's 102, it's using the same multiplier system that we just looked at. Of course, this means 1000. With higher precision resistors, you'll see 4 digits. For example, see 1001. Well, that means it's a 1000 ohm. You just add 10 to 100, so 1000. Difficulty in reading. That's one bugaboo that I have, and sometimes you have to be careful. It's very hard to read the colors on the blue metal film type resistors. Also, you have to be careful of the tolerance. For example, brown, black, red is normally a 1K resistor. With a precision resistor, it would be brown, black, black, brown, because you're only adding another 0. The point I'm making, if you're used to the normal 3-band plus the tolerance band type resistors, like this one here, and you go grab a precision resistor, you think, well, right off the top of your head, you're thinking brown, black, black, red would be 1K, but no, it's not. That's actually 10K. So you have to watch out for that. Another gotcha I have is these resistors where they just print the value right on there. If manufacturers are looking, do like they did with these resistors here. It's printed on 3 different positions. I've seen resistors where they print it on just one side and it might be towards the bottom and you can't see what the heck it is. Or, if the resistor gets warm, the ink they use will fade and become difficult to read. So they should use a thermally stable ink, and they should print it at different positions around the resistor like they did here, so you can read the darn thing. One question that some people have is, where do they come up with these weird values like 220 ohms, 3.3K, 47K? Why isn't it just 500K or 400K, 300K? Why is it these kind of odd values? And that's where the E range comes in. What they do is they use a formula to break up resistor values into a certain amount per decade that are spread evenly apart. For example, you'll have an E6 range. That means there'll be 6 different values per decade. You'll see an E12 or even an E24, where with E12 you'll have 12 different values per decade. So for example here, with the E12 range, you'll have all of these different values here. So, this is from 1 ohm to 10 ohms. And from 10 ohms, you'll have 10 ohms, 12 ohms, 15, all the way up to 100 ohms. And then you'll have 100, 120, and so on and so forth through the different decades. Another thing I should mention is the schematic symbol. This is the symbol that I like to use, the box shape, the IEC one. There's also the squiggly line one, or the ANSI one. So now let's take a look at the 5 common types of resistors. Like I said, there's other types, but these 5 are probably the ones you run into the most 99% of the time. First up is carbon composition. These, although they're still available, have fallen out of favor. Not as common as they used to be. They were very common. If you repair old radios and TVs and things, you see these used quite a bit in those devices. How they're made is you have the leads on the outside, and they put a mix of carbon or graphite mixed in with like a powdered ceramic, and depending on the ratio of ceramic to carbon or graphite is what makes its resistance value. So it must be a pretty precise mixing procedure to make that. And here is a carbon composition resistor. They're usually a cylindrical shape. This is a fairly large one, probably like a 5 watt or something, which is about the limit I believe they made them. And you can see where I broke it open, you can see the carbon ceramic powder mixture in here. And the lead just goes in, connects in here. They bend it over so the lead doesn't pull out. And pretty much how it works. The nice thing about carbon comp is, well, they're cheap and easy to make. And because there's not really any coil of wire inside. It's, the current mainly flows straight. They're pretty good with RF. However, on the bad side, they tend to be noisy. They tend to drift. If they get hot, they tend to be damaged or drift quite a bit. And I'm sure a lot of people who repair older electronics do find that these things have drifted in value. Next up is the carbon film resistor, and this is what this one is here. It's probably the most common through-hole type resistor today. It has that classic dog bone shape, and I made a little drawing here of this as well. The outer coating here is represented in the dotted line, and you can see how it gets the shape. You have two metal caps here on each end, and what they do is they put a thin film of carbon here, and they cut away strips of this, so you end up with a spiral, and depending on the spacing and how many turns, you end up with your given resistor value. The carbon film resistors tend to be better than carbon comp resistor. You can get higher precision with them. They can drift, but they tend to be more stable. But because of the spiral, it does act as a coil, which can be a problem with RF. But usually, the inductance that creates is very low. It's usually down in the nanohenry range, and doesn't affect the signal until you get into very high frequencies like VHF. However, it really depends on the resistor, and you should check with the manufacturer to be sure your resistor will work properly in a high frequency circuit. Let me put a magnifying lens in front of the camera here. We can get a close-up of a carbon film resistor. I've taken this one and sanded down one side. You can see the metal end caps. You can see part of that spiral of carbon. And the white line you see towards the right, that's probably the ceramic cylinder that the carbon is laid on when they make that spiral. So yeah, that's pretty neat. You can see how the resistor is constructed. Next is the metal film type resistor, and I have a couple samples here. These are 1/4 watt ones, by the way. This carbon film one was a 1/2 watt. See if I can get a close-up here. You can see what they look like at close range. They have a similar construction as carbon comp, really, so not much more to say. It's just that they're using a metal film. And again, under the magnifier here, you can kind of see the dashed area. It's metallic. You can see it reflecting the light. So you can see the similar construction. Metal film resistors are superior to carbon film in about every way. They're not as noisy. They can handle surges a little better. They can be higher precision. But with that spiraling, you might have an issue with RF, though these usually work at very high frequencies. I've read that it can be in the VHF range. But there's really very few turns, maybe 6 or 7 in this case. This is I believe this is a 20k ohm resistor. It's on a very small former. I would think that even the leads have more inductance than the small coil effect of the internal resistor design. Well, it's actually another day I'm shooting this, because when I was editing my video, my Wirewound resistor material was gone. Oh well, I guess that's the problem with video production. Some of your stuff disappears sometimes. I think I accidentally deleted it. But anyway, next up is Wirewound resistors. They usually come in different formats, like these square, porcelain type, various sizes for the different power dissipation. This is a 25 watt. This is a little 5 watt here. And they can also come in the smaller size. This is, I think it's a 1 watt. And what they do is, this is actually a ceramic coating. These are meant to operate at much higher temperatures. And they're called flame proofs. They don't have any coatings that can smoke or burst into flame. Well, I guess they can smoke a little bit when they get hot, but they usually don't burst into flame. I didn't do a drawing of this one. It's pretty large. You can see it has the metal end caps with a spiral of thin wire, and that could be an assortment of different materials, probably nichrome. This is in fact one of these, which I broke the outer casing off. Here's another one that's a 220 ohm, and see if we can get that in focus. Has really fine wire, so you can probably guess an issue with these. Well, with that much winding, that's going to be significant inductance. In fact, they can get up into a few millihenries of inductance in these because of that. So they could be limited from RF use, even lower frequencies. Now there are special types available, which we'll look at momentarily. They don't really have an issue with noise or drift because they're using a metal wire. It tends to be low in noise, and they're not going to drift. Because of the fine wire they use, tend not to be very high values. I don't know what the limit is, but you rarely see them at very high values. But of course, they're used where you need to dissipate a lot of power. Now let me show you one type of wire-wound resistor that's low inductance. If you notice here, there's one coil that's going clockwise and another one spiraling counterclockwise. This is called the Ayrton-Perry type winding. And I hope I'm pronouncing that correct, because it's somebody's name, you never know if it's right or not. But what happens is, when you have a coil going one way and another one going the opposite way, you're canceling out any inductive effects because the electric current is passing in opposing directions. You might say, well, don't they short at the crossover points? Well, because the coil is equally spaced, equal length, and same type of wire, these are equal potential points, so it doesn't matter. So you end up with a very low inductance, and really hated to bust open my low inductance 20 watt power resistor here, but it's pretty interesting to see this type of winding in use. Last but not least is the surface mount resistor, probably the most common today due to the use of surface mount printed circuit boards. And I don't have any free ones about, but we'll just look at one on a circuit board here. If I put the magnifier in front of the lens, you can see those little black devices there with the white numbers. Those are surface mount resistors using the code that I mentioned previously. So you can see there that one, the second up from the bottom there, that says 102 on it, is a 1K resistor. And if you look at the side of it, you might be able to see that it's white on the bottom. That's the ceramic substrate, and that black area is the resistor, actual resistive part of it. Here's a drawing I made of one. So you can see here, this is the ceramic, and they put a coating of resistive material here, and then there's like a glass-like coating they put on top of that to protect it, and then they print the number on the top, and of course these are the electrodes. Surface mount resistors have very good performance. They can be high precision, they're low noise, and because there's not a coil of the resistive material, there's not a big issue with inductance. And of course they can have a very small form factor. They can also use copper foil areas to help dissipate heat. Of course higher power ones are going to be larger in size, but yeah, they're very space efficient, not having those leads to deal with. Well, there you have it, a little in-depth look at resistors. Like I say, they can be a little more than meets the eye because of some of these issues you can run into. So, if you're designing a precision circuit, these can catch you off guard if you're not aware of them. And I hope it helps you out. Thanks for watching.